So I'm beginning with one molecule of glucose. The very first reaction in glycolysis is catalyzed by hexokinase, where glucose is phosphorylated to glucose 6-phosphate. This step costs 1 ATP. And then a little later, another ATP is consumed when phosphofructokinase 1 converts fructose 6-phosphate into fructose 1,6-bisphosphate. So before it produces anything, we're already down 2 ATP molecules. In the payoff phase of glycolysis, energy starts to flow back. Glyceraldehyde 3-phosphate dehydrogenase converts glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. In this step, 2 NADH are produced, one from each 3-carbon molecule. At 2.5 ATP per NADH, that's 5 ATP equivalents, later on in oxidative phosphorylation. Next, phosphoglycerate kinase transfers a phosphate from 1,3-bisphosphoglycerate to ADP, forming 3-phosphoglycerate. That gives 2 ADP directly. And then finally, pyruvate kinase converts phosphoenolpyruvate to pyruvate, producing 2 more ATP. So in glycolysis, it nets 7 ATP equivalents total, minus 2 ATP originally invested, plus 4 ATP produced, and plus 5 from NADH. Each pyruvate is then converted to acetyl-CoA by the pyruvate dehydrogenase complex. This step produces 2 NADH per glucose, which means 5 more ATP equivalents. Now, after that, we then enter the citric acid cycle. Inside the citric acid cycle, or TCA cycle, 4 major energy-producing steps occur per glucose. First, isocitrate dehydrogenase oxidizes isocitrate to alpha-ketoglutarate, producing 2 NADH worth 5 ATP. Second, alpha-ketoglutarate dehydrogenase converts alpha-ketoglutarate to succinyl-CoA, producing another 2 NADH. Again, that's worth 5 ATP. After that, succinyl-CoA synthetase converts succinyl-CoA into succinate. This step is special because it produces 2 GDP, which are equivalent to 2 ATP. And fourth, succinate dehydrogenase oxidizes succinate to fumarate, generating 2 FADH2. And each FADH2 is worth 1.5 ATP, so this yields 3 ATP. Finally, malate dehydrogenase converts malate to oxaloacetate, producing 2 NADH, which give another 5 ATP. We then add up the cycle's contribution. The citric acid cycle alone produces 20 ATP equivalents per glucose. So summing up from glucose to CO2, glycolysis contributes 7 ATP, pyruvate oxidation adds 5 ATP, and the citric acid cycle produces 20 ATP. So that brings us a total of 32 ATP molecules. However, in many eukaryotic cells, the 2 NADH from glycolysis are shuttled into the mitochondria by the glycerol 3-phosphate shuttle, which yields only 3 ATP instead of 5. In that case, the grand total would be 30 ATP molecules. So depending on the shuttle system, one molecule of glucose can generate between 30 and 32 ATP molecules. And that is how glycolysis, pyruvate oxidation, and the citric acid cycle work together to extract chemical energy from glucose. One of the diagrams I uploaded, which is one from the book, the diagram that ties everything together. Glycolysis at the top, pyruvate oxidation in the middle, and the citric acid cycle at the bottom. At each key step, enzymes are shown in blue, energy inputs or outputs are in red, and the green circles track the flow of carbon. By following the arrows, you can see exactly how glucose is broken down and how energy is captured as ATP, NADH, and FADH2 to fuel the cell.